All right, so this video is a follow-up to the last one. In this one, we're talking about molecular geometry. And for this, we analyze the number of outside atoms and number of non-bonding electrons. So this is the next step. We've already drawn a Lewis structure, we've determined electron geometry, and now we're determining the molecular geometry. So I've got a model here for my first situation where I have a center atom with two regions of electron density around it. And you see that these are both double bonds in this example that I'm showing you. But each one is considered one region of electron density. It is like, let me scoot back up here. It is like this drawing. Okay, so there's two regions of electron density here. They arrange themselves 180 degrees from each other. And when I look at the molecule as a whole, it's a linear molecule. They're all in one line. So if I have three regions of electron density, we talked earlier that would give us an electron geometry of 120 degrees apart. And I've got a model to represent that. Okay, so that's representing this line here. Three outside atoms. So all of these regions of electron density are bonding pairs of electrons with atoms that they're bonded to. And so I end up with a flat molecule, a planar molecule. I'm showing you the side view here. And it's a triangle, so trigonal planar. If I remove one of those atoms, if instead I had something like this generic form, where I've got two bonds to two atoms, like a single bond to two different atoms, and then a lone pair of electrons. Well, now in my model, I've taken off that third atom, and I've put in this paddle that represents a lone pair of electrons, that they're non-bonding electrons. So the electron geometry is still trigonal planar, but when we go to describe what the molecular geometry is, now we're just looking at what is the molecule itself look like. It's not linear, is it? It keeps that shape. It keeps that angle, and actually the angle changes just a little bit. When there were three outside atoms, it was 120 degrees. A non-bonding pair of electrons takes up a little bit more space. It repels those bonding pair of electrons just a little bit more, so we end up with a bond angle of about 118. They're pushed together just a little bit more. It's hard to show on my model set here. Okay, so the name for that, big and fancy name, bent. And then for four regions of electron density, let's scoot to this bottom line here first, and this is my model for it that we looked at in the last video. If all of the bonds go to outside atoms, all of the regions of electron density are bonding pairs of electrons, and I have four outside atoms, then I say the molecule as a whole is tetrahedral. But let's say that we have a situation where only three of those regions of electron density are bonds, and then I've got a lone pair. That would be like this. See, I've got my center atom with three regions of electron density that end in an atom, and one that is a lone pair of electrons that I'm representing with this paddle. So the electron geometry is still tetrahedral, but now to describe the molecular geometry, and I want you to appreciate here that that it is not trigonal planar like in our last one, but this has a different name. It's still a triangle shape here, so it does have trigonal, but now it's pyramidal. So trigonal pyramidal, where the three white atoms in this representation are all in one plane, Maybe if I hold it like this, you can see that. And then the center one, this blue one, is different. It's a little bit above that. If I set the three white ones on my table, the blue one has some space. So the name that we give that is trigonal pyramidal. And the bond angle, instead of the normal tetrahedral bond angle being 109.5, for the same reason as in the three regions of electron density where it got squished a little bit closer, same thing happens here. This lone pair of electrons takes up more space than if it was a bonding pair of electrons, so it decreases. And we say it's about a 2-degree decrease in the bond angle for every lone pair of electrons. So I would predict that this bond angle would be 107. And by bond angle, I mean from this white one to the blue to this white one. So that angle. Then if I've got a molecule where I have 4 regions of electron density, but only 2 outside atoms. Let me draw that and shift my paper here a little bit. If I have this, okay, now these are non-bonding pairs of electrons. These are 2 atoms, so that's represented by my molecule here. My center atom has 2 bonds to outside atoms and 2 pairs of non-bonding electrons. Well, then I say that my molecular geometry is bent and the bond angle is about 105. I've gone down a couple more degrees because now I've got 2 lone pairs of electrons taking up more space. So the remaining atoms get a little bit closer together because these repel just a little bit more than if they were bonding pairs.